Hello. Good evening, all. I am Saurabh. I welcome you to this live session for the course NPTEL course Applied Thermodynamics. In today's session, we will discuss some problems related to gas turbine cycles, specifically jet propulsion cycles. Okay. So, as we discussed, that gas turbines engines are either used for power production or for the generation of thrust. In case of aircraft, these engines are mainly used for generation of thrust. Okay, so in today's session, we will solve some problems related to jet propulsion cycles. Okay, so so let us begin with question number one. So question number one says the type of aircraft operating with gas turbine cycle include turbojet, turbofan, turboprop, or all of these. Okay, so we have to tell that the aircrafts which operate on gas turbine cycle. So what are the type of those aircraft? The types of aircraft we have to tell. So let us see all these options one by one. Turbojet, yes, there are some aircrafts which are which work on the turbojet engine. Some work on turbofan engine, some work on turboprop engine. Okay, turboprop. So all of these options are correct. Okay, so here are those types. Okay, so you can see here different components. Okay, so for example, this first one is turbojet engine. Okay, this is turbojet. These are types. This one is turbojet. Okay, so in turbojet, there is first of all there is a diffuser. Okay, then after diffuser, some usual components, and at the end there will be nozzle. Okay, so you'll get thrust. So in turbojet, there is no propeller or fan. Okay, but here in this turboprop, you can see there is a propeller, right? This propeller is there. Okay, and in turbofan, there is this fan, right? This is propeller. Here it is a fan, right? So this is turbofan engine, and here the turbojet engine with afterburner. Okay, so here it is afterburner. So for afterburner, we have adjustable nozzle. So whenever we require some extra thrust, we can inject fuel in the exhaust gases. Those exhaust gases which are coming out from the nozzle, they are quite hot, and if you inject some fuel in that hot gas, the fuel will burn and you will get some extra thrust. Okay, so to get that extra thrust, you need to adjust the nozzle shape. Okay, so you need adjustable nozzle. Okay, so these are different type of engines which are used in aircrafts. Okay, I hope this question number one is clear, that these are different types. All of these are different types of engines which are used in aircraft operating on gas turbine cycles. Okay, so if it is clear, then we will move to the next question. Question number two. Question number two says, in a gas turbine engine, the pressure loss in the combustion chamber is mainly due to non-adiabatic flow, turbulence, and friction. Okay, so as we know that if the cycle is not ideal, then there are several losses. Okay, losses occur in all the parts. Okay, in all the components. Losses occur in turbine, they occur in compressor, in combustion chamber, everywhere losses are there. So because of losses, the efficiency is reduced. Okay, so as far as losses are concerned in combustion chamber, then these are the main reasons. Okay, non-adiabatic flow, because of the non-adiabatic flow there will be heat loss. Because of turbulence and friction also there will be some losses. Okay, so this statement is true, right? The non-adiabatic flow, turbulence and friction, they will cause some loss. Okay, okay, so I hope this is clear and we will move forward. Okay, question number 3. It says, when a heat exchanger is added to an ideal gas turbine. Okay, so this is a heat exchanger. There is a heat exchanger added to a gas turbine cycle. Okay, so we have to tell that power output decreases but efficiency increases. Option B says power output increases but efficiency decreases. Option C says power output remains same but efficiency increases. And last part says efficiency remains same but power output increases. Okay, so first of all we should know what it is, how a heat exchanger is used in a gas turbine. We know that in a gas turbine the exhaust gases which are coming out, okay, they are quite hot. Okay, so they have a lot of heat energy, and you are just throwing that heat energy into the environment, and that heat is being wasted, right? So if somehow you can utilize that heat, then what will happen? Efficiency will increase, right? Because the heat input requirement will be reduced, right? So those hot gases, those hot gases are passed through a heat exchanger, and with the help of that heat exchanger, the initial temperature of the air is increased. Okay, so the total heat requirement will reduce because you are utilizing this heat of exhaust gases. Okay, so it is some sort of waste heat recovery. Okay, but it will not affect the total work output. Okay, so the total power output, that will not change. Okay, because you are not disturbing the turbine. Okay, so turbine is just functioning as usual. Okay, so there is no change in the total work output, but the efficiency will increase. Why? Because total work output is constant but total heat requirement, that is being improved, right? Because you are utilizing the waste heat of the exhaust gases. Okay, so option option C should be the correct option, right? Power output remains same. Okay, power output remains same but efficiency increases. Correct. Okay, there will be a compressor, then there will be a combustion chamber. Okay, so from combustion chamber hot gases will be expanded in a turbine. Okay, so those hot gases, they will be passed through a heat exchanger. Okay, so this gas will go into heat exchanger and it will got hot. Okay, so before passing into combustion chamber, these gases will go into heat exchanger. Okay, so they will get some heat from the heat of this exhaust gas, this turbine. Okay, this is heat exchanger. So part C is the correct option. Okay. So I hope this is clear, and we can move to the question number 4. Okay, so here some extra, information is given. This diagram is given for heat exchange cycle. So here you can see from 1 to 2, this is compression. If it was ideal, cycle, then from 1 to it would have been to 2s. Okay, isentropic compression, because of some irreversibility, it will not be an isentropic process. Okay, so from 1 to 2 it's compression, and 2 to 3 2 to 3 is the heating with the help of a heat exchanger. Okay, so from 2 to 3, okay, this is heating in heat exchanger. Okay, and 3 to 4 is our usual combustion in the combustion chamber. Okay, so from 4 to 5 or 5 to or sorry, from 4 to 5 or from 4 to 5s, if it was from 4 to 5s, then it would have been isentropic turbine, but in the real case there will be some irreversibility. So from 4 to 4 to 5, so this is turbine. So at the exit of turbine, the exhaust gases, they are quite hot. So with the help of these gases, you will preheat the air. Okay, so this 5 to 6, this is also heat exchanger. Okay, so efficiency of a cycle with heat exchanger is more than the simple cycle. Okay, here are some expressions which you can use to calculate the efficiency. Okay, and if it is clear, then we will move to the next question. One more point you can note here, that gases coming out from the compressor and before entering into combustion chamber, the temperature is raised only up to 0.3. Okay, but if this heat exchanger had very infinite effectiveness, okay, if it has 100% effectiveness, then the temperature will have reached up to 0.5. Okay, but in reality you cannot reach up to the maximum temperature. Okay, so if you are not reaching up to this point, right, so you are reaching only up to 0.3, because it does not have 100% effectiveness. Okay, and no heat exchanger will have that effectiveness. Okay, because for heat transfer you should have some finite temperature difference. Okay, so I hope this is clear, and we can move forward. Okay, question 4. It says propulsive efficiency of an engine. So it is saying either this propulsive efficiency decreases or increases or remains constant when the uh, aircraft velocity is increased. Okay, so we have to fill in this blank. So propulsive efficiency of an engine, some blank space, with the increase in aircraft velocity. So you have to tell that whether this efficiency increase or decrease or remain constant. So this have been discussed in the lectures, and I hope that you should be able to answer this question. So first of all, you should know what is propulsive efficiency. Okay, so propulsive efficiency is thrust power that you are getting divided by the total power that you might have got. Okay, so total power will be thrust power that you are getting plus unused part of the kinetic energy, right? So this is called propulsive efficiency. Sometimes also this thing is called, proud efficiency. So I have to tell that this thing increases or decreases when this aircraft velocity is increased. Okay, so I can write the expression. It is 2 divided by 1 plus Cj by Ca. So Ca is your, velocity of aircraft, and Cj, you can say the velocity at outlet or the jet velocity. So when the Ca will increase, then what will happen? If the Ca increases, then this thing will decrease, okay? And this n will increase, okay? So with the increase in aircraft velocity, this propulsive efficiency should increase, okay? We have a graph. I will show you that graph so that you can better understand, okay? So here is that graph. This x-axis shows the aircraft velocity, y-axis shows the propeller efficiency, okay? So you can see that this propeller efficiency increases. At least initially it does increase, with the increase in aircraft velocity, okay? So here are some points that propulsive efficiency increases with the increase in aircraft velocity, okay? So in propeller driven aircraft, the propeller efficiency is higher for propeller driven aircraft in initial stage up to the sonic, velocity, okay? So up to somewhere up to this point, the propeller efficiency increases, okay? Then it decreases, okay? So in jet driven aircraft, what happens? This is continuously increasing, okay? So jet driven aircraft becomes superior at higher speeds, okay? So above Mach number of 0.7, okay? So at the speeds more than 850 kilometer per hour, jet driven aircrafts becomes better, okay? Okay, so up to this range, sonic, this is something around 0.7 Mach number. Okay, so up to this point, the propeller efficiency is better, and then it decreases. Okay, so I hope this is clear. Propulsive efficiency increases with increase in aircraft velocity. Okay, so question number 5. It says, afterburners in aircraft engines are used to decrease the thrust of engine. So here in this picture, you can see there are some visible flames are coming out, right? These, so these are coming from afterburner, okay? As we discussed in some previous question, that exhaust gases are quite hot, and if you inject some fuel on in that hot exhaust, so you will get some extra thrust, okay? So sometimes we need some extra thrust. For example, uh, at the speed near the speed of sound, you will have to overcome a huge drag, right? Because in the sonic range, when the speed is quite near to the sound barrier, so at that, in that range, the drag force is very, very high. Okay, so overcome that drag, you need extra thrust. Okay, so then you will have to use the afterburner. Okay, so many times you use afterburner. Okay, so whenever you require extra thrust, you use afterburner. So afterburners are used to increase the thrust, not decrease. Okay, so this option is false. Okay, so in many pictures or many videos, you might have seen these visible flames. So this is not an accident. Okay, this is not the accidental fire. This is something coming out from the afterburner. Okay, I hope this is clear, and we should move question number 6. Question number 6 is that the ideal location for the placement of an intercooler in a two-stage gas turbine unit is in between what? A low pressure turbine and high pressure turbine, high pressure compressor and high pressure turbine, low pressure compressor and low pressure turbine, or low pressure compressor and high pressure compressor. Okay, so first of all, why we are using this intercooler? We are using this intercooler because after the compression, gases becomes very hot. Okay, and so density will of course reduce. So if you want to, okay, so because of that, the compression work will increase. So if you want to reduce the compression work, you should cool down that compressed gases. Or in the ideal case, if the compression is taking place at constant temperature or isothermal compression, then in that case the compression work is minimum. Okay, so in order to minimize the compression work, you want to, you know you are trying to make this process near to isothermal, but that is not possible. So what we do this compression in more than one stage. Okay, so there are multiple stages. Okay, so after each compression stage, you cool down the gases, compressed gases, and then again you pass those gases from you pass those gases through a compressor, and again intercooler. Okay, so like that this goes on. Okay, so using this concept, you basically try to minimize the compression work. Okay, so the intercooler is used between two compressors. Okay, so first compressor will be your low pressure compressor, and the second one will be your high pressure compressor. Okay, so the low pressure compressor, then high pressure compressor, and in between you will use a intercooler. Okay, yeah. So intercooler is used between low pressure compressor and high pressure compressor. Why? Because to reduce the total compression work. Okay, okay, so here is a better diagram. So as you can see that air comes and it passes through low pressure compressor, and this low pressure compressor is connected to a high pressure compressor with the same shaft. Then the air which is coming out from the low pressure compressor, then it is going through a intercooler, right? So this will become cool. Then this cooled air will be passed through high pressure compressor. So using this technique, you basically reduce the compression work. Okay, then after high pressure compressor, you have your usual cycle. Okay, so the compressed air will go inside combustion chamber, where the fuel will be injected and combustion will take place, and the hot gases will expand in turbine. You will get the work output. Okay, so this is the location between low pressure compressor and high pressure compressor where the intercooler is used. Okay, so I hope this is clear, and we will move to question number next question 7. Okay, in this question answer is also given. Anyways, we will just read the question and answer. Question number 7 says isentropic efficiency is defined in terms of what, and RAM efficiency is expressed in terms of something. I mean, you have to fill in the blank. So these are two methods by which the efficiency of intake system are analyzed in a turbojet engine. So answer is given that isentropic efficiency is defined in terms of temperature rise, and RAM efficiency is expressed in terms of pressure rise. And these efficiencies are a representation of how well the intake system is working. Okay, so these are the method by which the efficiency of intake system in case of a turbojet engine is analyzed. Okay, so what basically is a turbojet engine? So that we will see in this question 8. In a simple turbojet engine, so a simple turbojet engine is basically what? A propeller system or a gas turbine engine equipped with a propulsive nozzle and diffuser, or chemical rocket engine or ramjet engine. So turbojet engine. So in turbojet engine, we have a diffuser and we have a propulsive nozzle. Okay. So we have seen this turbojet engine in some previous question. We had a diagram. Okay. So here is the turbojet engine. Okay. So here we have diffuser, inlet, and then we have a nozzle. Okay. So this is our propulsive nozzle. Okay. So this is a turbojet engine. Okay. So turbojet engine basically is a gas turbine engine which is equipped with a propulsive nozzle and a diffuser. Okay. This was question number 8, and we will move to the next question. So question number 9 says an aircraft powered by ramjet engine requires auxiliary power supply to attain velocity necessary for starting off engine through ram compression. So answer is yes. It does require some auxiliary power supply so that the velocities are enough so that engine can be started using the ram compression. Okay, so in ram compression, basically the air is compressed, but for the compression you need high speed air. Okay, you need kinetic energy. Okay, to get that high speed air you need some extra equipment, some auxiliary power supply, so that you get the necessary velocity. Okay, so basically the compression takes place with the help of kinetic energy. Okay, so first you should have kinetic energy, and to attain that kinetic energy you should have some auxiliary power supply. Okay, so this is basically how a ramjet engine uh, start. Okay, so yes, this is true statement. Okay, so we will move to next question. Question 10. It says which type of compressors are used in turbojet. So mostly axial compressors are used in turbojet. Okay, we do not use, reciprocating compressors, because axial compressors provide more, you know, mass flow rate. Okay. So question 11. So in question 11, there are two statements are given. So first statement says the fluid velocities are generally high in turbo machine. And statement 2 says, sorry, the changes in kinetic energy between inlet and outlet of compressor and turbines cannot be neglected. So we have to tell that if both statements are correct or both are false, or one of them is correct and another is false. So let us see both statements one by one. So the first statement, which says the fluid velocities are generally high in turbo machines. Yes, we are dealing with quite high fluid velocities. Sometimes we also go in supersonic ranges. Okay, so they are quite high velocities involved. So this is true. And second statement, changes in kinetic energy between inlet and outlet of compressor and turbine cannot be neglected. Yes, we cannot neglect the changes in kinetic and you know kinetic energy at inlet and outlet, because there is huge difference. So this is also correct. So both of them are correct. Option A should be the correct option. Okay. So now we can move to the next question, question 12. Which among the following engine operates on aircraft propulsion cycle? Turbojet, turbofan, turboprop, or ramjet? We have seen the pictures of these engines, turbojet, turbofan, and etc. So we have to tell that which of these engines operate on aircraft propulsion cycle. Turbojet, yes, it does work on aircraft propulsion cycle. Turbofan also work on aircraft propulsion cycle, and turboprop and ramjet also work on the aircraft propulsion cycle. Okay, so all of these are correct. Okay. Sorry. Okay. So question 13. Question 13 says that the thermodynamic process occurring in turbo machines are mostly adiabatic and their ideal processes are isentropic. So yes, it is correct. In combustion chamber, of course, there is heat transfer, heat addition, so that is not adiabatic. But compressor and turbine, there we assume that the process is isentropic. But in real case, the process will involve some irreversibilities, so that will not be isentropic. But their ideal counterpart, okay, their ideal process will be isentropic and adiabatic. Okay, so there can be some heat losses, but it is written mostly adiabatic. So yes, they are mostly adiabatic, and if it would have been a ideal process, then it would have been isentropic as well. Then there would have been no irreversibility. Okay, so yes, this is a true statement. Okay. So compressor and turbine. These are adiabatic, mostly adiabatic, because there will always be some little heat loss. And in ideal case, this will be process will be asentropic. Okay. So now we can move to the next question. Question 14. Okay. So this is subjective question, numerical question. We will read this question. It says that a turbofan operating on an aircraft flying at 200 meter per second, okay, at an altitude where the air is at 50 kilopascal and 220 degrees Celsius. Okay, so when you go higher than at some altitude, the density of air reduces, and the air pressure, the atmospheric pressure also reduces. So it is flying at some height, and at that height the pressure is just 50 kilopascal. Okay. And temperature is 220 degrees Celsius. So I think there is some mistake, because at higher altitude the temperature should be very very less. It is in some negative degree Celsius. Okay. So this should not be 220. This should be some negative. Okay, let us proceed with minus 20 degrees Celsius. Okay. Okay, so the air pressure is 50 kilopascal and temperature is minus 20 degrees Celsius. So the turbofan engine operating on an aircraft flying at this speed, the air pressure is 50 kilopascal, temperature minus 20 degrees Celsius, is to produce 50,000 Newton of thrust. The inlet diameter of this engine is 2.5 meter. The compressor pressure ratio is 12, and the mass flow rate ratio is 8. We have to find the air temperature at fan outlet needed to produce this thrust, and we can assume the ideal operation for all components at constant specific heat at room temperature. Okay, so we have a turbofan engine first of all. So in a turbofan engine you have a fan. Okay, so some part of the air will go into the this combustion process. Okay, the thermodynamic cycle, and the remaining air that will bypass. Okay, so that ratio is the mass flow ratio. Okay, so that ratio is 8, and it is flying at 200 meter per second altitude speed, and pressure is given and the temperature is given. Okay, so let us proceed. Okay, so we will take some assumptions. First we will take that the whole process is this aircraft is flying at some steady condition. Okay, okay. And it is also given that we can assume ideal operation for all components, and constant specific heat at room temperature. Okay, so we will use the specific heat at room temperature. So at room temperature, this R, the universal constant, is 0.287 Pascal meter cube per kg Kelvin. These values are at room temperature, and we will use the same values because it is given. Cp is 1.005 kilojoule per kg Kelvin, and K, or sometimes you write it as gamma. This we will take 1.4. Okay, and we can also assume that turbine is producing just enough power to run the compressor. Okay, so the compressor work is equal to turbine compressor work input is equal to turbine work output. Okay, so what we have to find? First, we should find the mass flow rate. Okay, the mass flow rate is what? Rho A V. Okay, so rho is density, A is the area, cross section area, and V is the velocity, inlet velocity. Let us write it VA1. So area you can find from the diameter because diameter is given. So area will be pi d square by 4. Velocity is given 200 meter per second. Okay, so pi by 4 and d diameter is 2.5 meter square. Okay, so we have A, we have V. We need to find this density rho. So we can find from ideal gas equation. Okay, so this is also one more assumption that we are using. We are assuming ideal, we are taking ideal gas assumptions. Okay, so we can use ideal gas equation. P is equal to rho RT. Okay, or P is equal to RT by V, small v, that is specific volume. Okay, okay, so P is equal to RT by V. So V we can write it as this. All these things are at inlet. Okay, inlet of compressor. First we can also make a diagram. TS diagram. So 1 to 2 is isentropic compression. 2 to 3 is your combustion chamber. So constant pressure heat addition. 3 to 4 is your turbine, and 4 to 5 is your nozzle. Okay, so this thing we are calculating at the inlet of compressor. Okay, so we can write V equal to RT by P. Okay, and if you substitute the values, R is equal to 0.287 and temperature is how much? Minus 20 degrees Celsius. Okay, so T1 is minus 20 degrees Celsius. That is equal to 273 minus 20 Kelvin. So 253 Kelvin. Okay, 253. Everything is in SI unit. So I'm not writing the unit. I will just write the final unit. Okay, so this we are calculating V, and the unit of V is meter cube per kg. And pressure was how much? 50 kilopascal. Okay, so if you calculate this value, you will find this value comes out to be 1.452 meter cube per kg. Just please check this numbers, the calculation. If there is any mistake, just let me know. Okay, so now you have density or specific volume. So now you can calculate the mass flow rate. Okay, so the mass flow rate is what? Cross-sectional area into inlet speed divided by the specific volume. Okay, so area is pi by 4 into 2.5 square meter square. Okay, into velocity is 200 meter per second. Again, everything is in SI unit, so I'm just writing the final unit. Okay, so and divided by the specific volume 1.452. Okay, so if you use your calculator and try to find this value, square into 200 divided by 1/4 from pi by 4 into 1.452. Again, I don't know why. Pi into liters. Pi into 2.5 square into 200 divided by 4 into 1.452. Okay, so it is coming out to be 676.1 kilogram per second. Okay, so this is our mass flow rate. Okay, in question, what was given? Mass flow rate ratio was given, right? Mass flow rate ratio was given, and it was 8. Okay, so it is defined as total mass divided by how much mass is going, in the process, combustion process. Okay, so this was 8. Okay, so from here you can find this ME, that will be divided, it will be equal to total mass flow rate divided by mass flow rate ratio. So 676.1 by 8 meter per second, kg per second. And if you calculate this value, then you'll get how much? 64. This is the mass which is going inside the combustion process. Okay, so the remaining mass, okay, so I will just make this some sort of record. So this is pen. So here the total mass is coming, and here ME will be going, and in the remaining volume, okay, in this area, okay, what will be the mass here? Here it will be M minus ME, right? So this will be equal to 676.1 kg per second minus 84.51 kg per second. Okay, so if you calculate this value, this is coming out to be, this is mass flow rate in the pen. Okay, so this comes out to be 591.6 kilogram per second. Okay, okay, so it was given that it is required to produce 50,000 Newton thrust. Okay, so thrust is given by rate of change of momentum, right? So that is equal to mass flow rate into change in velocity, right? Because mass flow rate is constant, so whatever the momentum is changing, that will be changing because of change in velocity. Okay, so mass flow rate into velocity at exit minus velocity at inlet. Okay, so this F is given, right? So from this expression, you can find the velocity at exit, because velocity at inlet is given 200 meter per second. Okay, so from here you can find the velocity at exit, so that will be equal to F divided by mass flow rate plus velocity at inlet, and all these values we already have. F, the thrust, that is given to be 50,000 Newton. Again, everything is in SI unit, so I'm not writing the unit again and again. Plus velocity at inlet was 200 meter per second. Okay, so we are getting 284.52. Or just take one digit, meter per second. Okay, okay, so this is the velocity at exit of the fan. Okay, so now we can do energy conservation. Okay, energy balance. Energy balance on the air which is passing through the fan. Okay, so from energy balance we can write it as Cp T4 minus T5. So what is T4? T4 is the inlet of nozzle or the exit of turbine, and T5 is the outlet of the nozzle. Okay, so that will be equal to square of velocity at exit minus square of velocity at inlet divided by 2. Okay, so what we have to find? We have to find the air temperature at fan outlet. Okay, so we have to find T5. So T5 will be equal to T, this quantity. Okay, so now we have all these values and we need to just substitute. Okay, T4 is outlet temperature, so that is 253 Kelvin minus, sorry, minus 284.5 meter per second square of this minus 200 meter per second square of this divided by 2, and Cp is 0.005 kilojoule per kg Kelvin. And this is kilojoule, so we can just write it as kilojoule, and we can divide it by 1000. Okay, meter square per second square kilojoule per kg. And if you calculate this value, then you'll get what? T5. So temperature at the exit of fan. Okay, the outlet of fan. So I'm getting 232. You please check this number, and if you are getting something else, then please let me know. Okay. So this is the temperature at fan outlet. Okay, and this is the answer. We had to find the temperature at fan outlet. Okay, I hope this is clear, and we can move to the next question. Okay, question 15. It says that a pure jet engine propels an aircraft at 240 meter per second through air at 45 kilopascal, and temperature is 213 degrees Celsius. So again, there is mistake. So it should be minus 13 degrees Celsius. Okay. The the inlet diameter of this engine is 1.6 meter. Okay. The compressor pressure ratio is 13. The temperature at turbine inlet is 550 degrees Celsius. We have to find the velocity at the exit of engine's nozzle and the thrust produced. And we can assume the ideal operation for all components and constant specific heat and at room temperature. Okay. So first we will make the TS diagram for you know this pure cycle. Okay. So this is our TS diagram. From 1 to 2.2 there will be diffuser, 2 to 3 compression, 3 to 4 constant pressure heat addition. Okay. Then 4 to 5 will be our turbine, and then the nozzle, 5 to 6 the nozzle. Okay. So we are assuming everything ideal. So this is isentropic process. So we put this diagram. Okay. So again, there will be some assumptions. One assumption is that the air which is coming out from the diffuser, that will be at very, very, slow speed. Okay. So that speed you can neglect with respect to inlet velocities and other velocities. Okay. The inlet velocity will be equal to the aircraft velocity. In the reference frame of aircraft, you can assume the aircraft to be at rest, and air can be assumed to be flowing at this speed 240 meter per second. Okay. So the velocity at diffuser outlet. Okay. So velocity at diffuser outlet, that is very, very small. Okay. So V2 is very, very small. Okay. And velocity at inlet, that will be equal to the aircraft velocity. Okay. So 240 meter per second. Okay. So in diffuser, you can use, energy balance. Okay. In the steady case, there will be whatever energy is going in, that will be equal to energy out. Okay. So if you do energy balance for diffuser, you will get energy in equal to energy out, right? So energy in is your H1 enthalpy. Okay. Everything is per mass basis. Okay. Per unit mass basis. V square by 2, that will equal to H2 plus V square by 2. And V square by 2 can be neglected because that is very, very, small. Okay. So whatever we have is H2 minus H1 is equal to V1 square by 2. Okay. And this H can be written as equal to CPT. Okay, so H1 will be equal to CPT1 and H2 is equal to CPT2. So Cp can be taken common. So H2 minus, sorry, T1 minus T2 will be equal to V1 square by 2. Okay. So T1 we have, right? T1, how much is the T1? Minus 13 degrees Celsius. So that is equal to 260 Kelvin. Okay. So T1 we have, V1 we have, Cp we can take the room temperature value. Okay. And V1 we have, T1 we have, Cp we can take the room temperature value. So you can calculate the T2. Okay. So from here, you can calculate T2. Okay. So T2 can be calculated as T2 is equal to V1 square by 2 Cp plus T1. Okay. Okay. So just substitute the values and you will get the T2. If you put the values, so 240 meter per second, 2, and the Cp value you can take 1005. Everything is in SI units, so I'm not writing the units, just final unit I will write. Okay. Plus 260 degree, 260 Kelvin. Okay. So if you calculate this value, you will find that okay. So this is T2. And this is diffuser, and we are assuming the process to be isentropic, so you can use the adiabatic relation. Okay. P1 V1 is equal to P2 V2 gamma or K, whatever you write. Let us write K. Okay. So and using the ideal gas relation, you can find the pressure. Okay. In terms of temperature, if you write, then you can write it as P2 is equal to P1 T2 by T1 to the power gamma minus 1 or K minus 1, whatever. So if you substitute the values, again, everything is in SI units. So P1 was 45 kilopascal. T2 we have just found out to be 288.6 Kelvin, and T1 was 260 Kelvin. to the power 1.4 divided by 1.4 minus 1. So it is 0.4. And if you calculate this value, then it comes out to be 64.88 kilopascal. Okay. So please check these values. If you are getting something else, then let me know. Okay, so we have temperature and pressure at the diffuser outlet. Okay, so after diffuser we have what? Compressor, right? Okay, so what is given about compressor? So compressor pressure ratio is 13. Okay, so this means P3 by P2 is equal to 13. So P3 will be equal to P2 into 13 or 64.88 kilopascal into 13. So we have P3 equal to 843.5 kilopascal. Okay. Similarly, since the compressor we are assuming to be working on an isentropic process, so you can use that adiabatic relation. Okay, so you can find the temperature as T3 is equal to T2 into P3 by P to the power k minus 1 by k, and if you substitute the values, you will get it as T3 equal to T2. What was T2? T2 was 288.7 Kelvin into P3 we have just found out, and so it is 483.5 kilopascal, and P2 was P2 what whatever P2 was 64.88. And anyways, this is P3 by P2 is your compressor pressure ratio, right? So it is 13. So we just need to find this value. K is 1.4. So 1.4 minus 1 divided by 1.4. Okay. So again, if you find this value, so it comes out to be 28.7, 13. Okay. So T3 is equal to 600.78 Kelvin. Okay. So we had diffuser, we had compressor. So after compressor, we have boiler. Sorry, that this combustion chamber. Okay. But combustion takes place at constant pressure. So pressure at 0.4 will be equal to pressure at 0.3. Okay. So P4 will be equal to P3. Okay, so then we have turbine. Okay, okay, so for turbine again we will use the same assumption which we used in the previous question, that turbine is producing just enough power to run the compressor. Okay, so we are making the assumption that turbine work output is equal to compressor work input. Okay, so we can write as compressor turbine work output is equal to H4 minus H5, and compressor work input is H3 minus H2. Okay, okay, so in terms of temperature you can write as Cp T4 minus T5 is equal to Cp T3 minus T2. Okay, so Cp will cancel out from both sides. So we have T2, we have T3, we have T4. So T5 we can find it as T5 is equal to T4 minus T3 plus T2. And if you put all these values, you will get how much is T4? T4 is 557 degrees Celsius. Okay, so 550, sorry, 557 degrees Celsius, but we need it in Kelvin. T4 minus T3 is 600.7 plus T2. T2 is 288.7. 88.7, and this value will be in Kelvin. Okay, so five five seven plus 273 minus 600.7 plus 288.7. So T5 is coming out to be 518 Kelvin. Okay, okay, so after turbine what we have nozzle. Okay, you just, I will write the whole chronology first. 1 to 2 we had diffuser. 2 to 3 we had compressor. 3 to 4 there was combustion chamber. 4 to 5 there was turbine, and 5 to 6 we have nozzle. Okay, so we had done turbine. Now comes the nozzle. Okay, so nozzle also we can use the energy balance. Okay, so neither it is energy consuming or nor energy producing, so we can use the energy balance. So energy in equal to energy out. Okay. So for energy in, we can write H5 plus V5 square by 2 is equal to, at outlet, we can write as H6 plus V6 square by 2. Okay. So we can write as H5 minus H6 is equal to V6 square by 2 minus V5 square by 2. And we know that the velocity at nozzle outlet is very, very high as compared to velocity at nozzle inlet. Okay. So V5 is very, very smaller as compared to V6. And the square of V5 will be even more small as compared to square of V6. Okay. So this thing you can neglect. Okay. V5 square can be neglected in comparison with V6 square. Okay, so this will be approximately equal to V6 square by 2. Okay, and this H values can be written in terms of temperature. So Cp T5 minus T6 equal to V6 square by 2. Okay, so T5 we already know, T6 we need to find. Okay, Cp we have, T5 we have, we need to find T6. So again, since this nozzle is an isentropic device, so we can use adiabatic relation. Okay, so T6 will be equal to, okay, from 4 to 6, this whole process is isentropic. Okay, 4 to 5 was turbine, that was also isentropic, and 5 to 6 the nozzle is also isentropic. So from 4 to 6 the whole process, both processes are isentropic, so we can directly use this relation. Okay, because the pressure value at 0.4 we know. Okay, and pressure at 0.4 is equal to pressure at 0.3. Okay, so T6 is equal to T4 into P6 by P4 into K minus 1 by K. Okay, we just substitute the values. T4 we have, where's T4? Okay, this is T4. 557 plus 273. Into P6 is the ambient pressure, okay, atmospheric pressure, and that is 45 kilopascal, that is given in question. And P4 we have calculated, right? P4 is equal to P3, and P3 is 843.5. to the power 1.4 minus 1 divided by 1.4. Okay, now we just need to calculate this value. This will be in Kelvin. Okay. If you calculate this value, then it will come out to be 359.3 Kelvin. Please do your own calculation and just check if you are getting the same value. If there is any discrepancy, just let me know. Okay, so now we have T6. T6 is coming out to be 359.3 Kelvin. And we can substitute this T6 value in this expression. Okay. So this expression now becomes, we will just copy once. Cp T5 minus T6 is equal to V6 square by 2. Okay. So from here, you can find V6, and that will be equal to 2 Cp T5 minus T6, the square root of this thing. Okay. And you substitute all those values. So we'll get 2 into Cp is 1.005 kilojoule per kg Kelvin. Then 580 Kelvin minus 359.3 Kelvin, and you convert everything is in data segments. You have multiply by 1000 kilojoule per kg. Okay. So this is V6. If you calculate this value, then it will come out to be, I'm writing the final value. It is coming out to be 564.8 meter per second. Okay, V6. So V6 is nothing but the exit velocity. Okay. Okay. So what was asked in the question? We had to determine the velocity at exit of this engine's nozzle. So this we have found, and this is nothing but V6. And we have to find the thrust produced. Okay. Now we need to calculate the thrust produced. Thrust, is rate of change of momentum, and that is equal to mass flow rate into exit velocity minus inlet velocity. Okay. We know velocity at exit. We also know velocity at inlet. We need to calculate the mass flow rate, right? And mass flow rate will be equal to area into velocity into density. So whatever, and we can assume the mass flow rate to be constant, okay, because it is a steady process. Okay, so we are not assuming, it is the the reality. Okay, so let us calculate this value at inlet. Okay, so area will be equal to pi by 4 into diameter square, and rho will be equal to p by rt, right? Or in terms of specific density, we can write it as rt by p. Okay, so specific volume at inlet will be equal to R into inlet temperature into inlet pressure. Okay, so this T1 and P1 are the temperature and pressure at ambient. Okay, so you just substitute the values and you can P1 is equal to 287 kilopascal per cube, 260 Kelvin divided by ambient pressure was 45 kilopascal. Okay, now you can use your calculator and calculate this value. The value I have here is V1 is equal to 1.658 meter cube per kg. Okay, so the mass flow rate, you can write it as area into velocity divided by specific volume. So area is pi by 4 into d square into V1 by, if you substitute all these values, then you will get pi by 4 into diameter was 1.6 meter, okay, into velocity at inlet or the aircraft velocity, that will be same as inlet velocity, that was 240 meter per second, and specific volume we have calculated, it is coming out to be 1.658 meter cube per kg. Okay, so if you calculate this whole value, then it is coming out to be, I'm writing the final value, it is coming out to be 291 kilojoule per second. This is mass flow rate. Okay, so now you have mass flow rate, you have inlet velocity, you have exit velocity, so now you can calculate the thrust. Okay, so thrust okay, so mass flow rate is 291 kilogram per second. Velocity at exit was 564.8. Velocity at inlet was 240 meter per second. So again, we just need to substitute the values and we'll get it. Okay, so it is, I'm writing the final value. Please check the final answer. It is coming out to be 94,520 Newton. Okay, so this is our final answer. This is the thrust generated, and this is the exit velocity. So I hope this is clear. This was question number 15. So when you solve a numerical question, all the processes becomes clear. Okay. So if you are able to solve the numerical questions, the subjective questions, then the objective questions are easy to solve. Okay. There are a few more questions, but I think this is enough for today. But just will read out the questions and you can note it down, and I will encourage you to solve it by yourself. And if you find any difficulty, we can discuss these questions in the next session. Okay, I will read out this question. Question number 16, it says the specific power output of a turbine is 336.5 kilojoule per kg, and the exhaust gases leave the turbine at 700 Kelvin. Okay, for a given value of Cp and Cv. Okay, these are the Cp and Cv values. We have to find the turbine pressure ratio. Okay. Okay. So you have to find the turbine pressure ratio. So a specific power output is given, outlet temperature is given, Cp and Cv are given. So you can find the pressure ratio. Okay, turbine pressure ratio. I will tell you the values. So this should be in the range of 3.5 to 4.5. Okay. So you will get your answer in this range. So if you find any difficulty, you can solve, you can discuss in the next session. We have one more question, question number 17. And it says the air, the properties of air are given, Cp is given, R is given, gamma is given. The air enters the compressor in an ideal reversed Breton cycle. Okay, so I think this ideal Breton reverse Breton cycle, you know, if you don't know, then you can refer any standard textbook. This is basically used for, cooling, okay, for refrigeration. Okay, because you know that the power cycle, if you reverse the power cycle, then what will be happen? Then what will happen? You'll get the cooling effect, because in power cycles you are putting some heat and you are getting the work output. In the reverse of any power cycle, you put some work and what you get, you extract the heat. Okay, so you take the heat from the colder environment and you put that heat into the hotter environment with the help of some external work. Okay, so that is your reverse of any power cycle. Here it is given the reversed Breton cycle. Okay, so reverse Breton cycle is also one type of a refrigeration cycle. So air enters the so components are basically similar. Okay, so the air enters the compressor in a reversed Breton cycle at 1 bar and minus 5 degrees Celsius with a flow rate of 1.8 kilogram per second. The compressor pressure ratio is 2.5 and the turbine inlet temperature is 25 degrees Celsius. We have to find the coefficient of performance of this cycle. Okay, so you know that for refrigerators we have coefficient of performance. Okay, that is equal to the heat removed divided by the work input. Okay, so you have conditions at inlet, you have flow rate, you have pressure ratio, you have inlet temperature, you have properties of air. So from the concept of your basic thermodynamics, you can calculate this. Okay, so what you need to do is, first you need for coefficient of performance, you need work input and heat removal rate. Okay, and coefficient performance is the ratio of heat removal to the work input. Okay, so I hope you can also easily solve this question. If you find any difficulty, we can discuss this in the next session. Okay, so this was our session 9 for gas turbine cycle, specifically the cycles related to aircraft propulsion. Okay, I hope you understood all the questions, and I hope this session will help you in solving your assignment problems. Okay, so we will stop here and we will meet in the next session. Okay, till then, thank you and take care.